Hello, everyone. My name is Xiaochuan Yang. I am going to be the instructor of the course PDE II for the rest of the semester. So it remains basically just one semester about distribution theory. So this will be the focus of the upcoming 7 weeks. The first, so actually before the Easter holiday, some of the material on distribution theory has been already covered. So to make my lectures as self-contained as possible, I'm going to make a short review about the material covered before the holiday. So the first thing would be the definition of test functions. So let's look at this test function. So we define U. We obviously use U to denote an open set in open subset of RD, and the function is called the test function if this function is C infinity with compact support in U. So the space of test functions is denoted by this du or C infinity 0 of U. So the topology of this space D of U is quite complicated. However, it is not very hard to describe the sequential convergence in the space of test functions, and this is given by the definition 1.2. We say that a sequence phi j in du converges to phi in D in D. Phi also a test function in the du sense. If there are two things, if there exists a compact set such that the support of all the functions in the sequence is included in K. And secondly, for any multi-index, it's a typo, alpha, the partial derivatives of phi j converges to the partial derivatives of phi uniformly. So with this definition in hand, we can define distribution. So distribution would be very simple. So this distribution, we use the notation, always use capital T to denote a distribution. So a linear form T is a distribution if it is continuous in the sense that the T applied to phi j converges T applied to phi whenever phi j converges to phi in the space D of U. Or equivalently, because we have a linear function, we have a linear form, so when we subtract this form, when we compute the difference of these two, it really means that it suffices to define this definition, define the notion of convergence for phi j. Here's typo. Phi j converges to 0. As the family of linear form, we actually naturally define a vector space, and this vector space will be denoted by d prime of U. Okay, so this definition with this definition, actually you can check right away that a distribution associated with a function, right? So this little f is a function defined in such a way. So this gives us a linear form, and we can check that this linear form is actually a distribution in the sense of definition 1.4. So this will be the case if f is a continuous function, and with a little bit of more effort, and you have seen it how to do that. Actually, we need modification. We can show that for generic integrable function with compact support, locally integrable functions, right? Denoted by L1 log, we can also show that all the locally integrable functions defined in such a way give rise to a distribution. So clearly the second definition is okay. So Clearly, a continuous function is a subset of the L1 log functions. So we have defined this distribution in a larger, we have a larger space, which are all distributions. So by identifying each of the L1 log functions with TF, which is the distribution given by this form, then we can say L1 log is a subset of the distribution of the it's a subset of all the distributions. Okay, subset of D prime. However, the space of distribution is much larger than L1 log, and in order to show that, we can make use of the following quite handy criteria, which proves that a linear form is a distribution. So this is actually equivalent to the definition of a distribution. So T is a linear form, and it will be a distribution if and only if that there exists a compact set. If and only if that for any compact set K in U, there exists a constant in M which might depend on K, such that for any phi with support in K, there's another typo. The absolute value of T applied to phi is bounded, have this upper bound, this inequality is satisfied. Okay, so this is quite useful because it allows to show more examples more examples of distributions. So here's another class of example. First of all, we can associate every positive Rodin measure with a linear form by using this integral. Okay, and it will be a distribution. It will be a distribution by realizing that the absolute value of T mu applied to phi is bounded by the measure of the support of phi. So this is a finite constant because the support of phi is a compact set, and the Rodin measure is Rodin measure has compact has finite mass, assigned finite mass to all the compact set. So this is a positive and finite constant, and this one is the uniform norm of the function itself. Okay, so in particular, we can this means that we have the m equals to 0 in proposition 1.5. So this shows that we have a distribution. Another distribution that I would like to point out is not locally integrable, right? So this is actually the idea is to consider a 1 over x function, and this time it is actually called a Cauchy's principal value, denoted by PV 1 over x, and this defines also a distribution, although it is not a L1 log function. So this example was not covered before the holiday. So let me briefly work it out. So by the definition, what happens? Yeah. So by definition, PV x phi is given by the limit epsilon goes to 0, then we consider x larger than or equal to epsilon, phi of x dx, right? So it is a linear function, so this is clear. And in order to show that it is a distribution, we're going to again make use of the proposition 1.5. First of all, let me compute the value of this integral when the domain is chosen to be those x with absolute value larger than or equal to epsilon. Okay, so since we remove the singularity, which is at 0, this is a well-defined object, and let's rewrite it. We can separate the domain in two parts. first part, negative infinity to negative epsilon. So we have 5x over x dx. And the second part is for epsilon from epsilon to infinity and 5x dx. And let's make a changeable variable for the first integral, and we're going to have infinity epsilon 5 negative x. Okay, so x dx. And since we don't want to have this kind of domain, so we want to have the lower the domain, the left-hand point of the domain is smaller than the right-hand point of the domain. So let's rewrite it. It becomes epsilon infinity negative plus epsilon infinity 5x over x dx. All right. So now we have one integral only, and we can put things together. We have this form. And now we see that this guy is converging. If we take epsilon go to 0, is converging to this integral. Okay, and the last convergence is justified by the dominant convergence theorem. Because so we have this indicator which is x larger than epsilon, and times phi of x minus phi of negative x over x absolute value, which is dominated by, so we can erase the indicator function. Then we have phi, by using mean value theorem, we see that this is actually bounded by twice phi prime the uniform null. Okay, and also don't forget about the domain, the support of this function phi, because otherwise, if we consider x outside of the support of the function phi, the left hand side will be 0. So let's put an additional indicator, which is support of the function. Okay, let's say let me be more precise, negative k x, where where the support of phi is included in this compact interval. Okay, so this actually finished the exercise because we know now that we have this inequality, and this inequality can be used to justify that, to justify the following. Hence, PV1 over x phi absolute value is bounded from above by this quantity, first of all, right? So because we have so this is, let me just actually have more than bounded. It is actually identity, because this guy is the limit of that, and we have shown that this limit would be this value. Okay, so phi of negative x dx, right? And this is bounded by, according to our inequality star, we have this 2k phi prime for by star, and this applying proposition 1.5, Ends the proof. Ends the proof. Okay, we are actually showing that this defines a distribution. Right. Okay, so this is the this is it. This is the first section where we have introduced the notion of, okay, let me recap. The important notion in this first section would be the definition of a test function, the space of test function, and the convergence of test function, convergence of this test function. And then the notion of a distribution, which has to be a linear form and continuous in some sense. And many examples we know that distributions are associated with L1 log function is a distribution. But more than that, we also know that the distribution associate the linear form by defined by using a Radon measure is a positive Radon measure gives rise to a distribution, and Cauchy's principal value, which is a typical example of a non-local, which is a typical example of distribution which is not associated with L1 log function. Okay, so this is the review part. So in what follows, I'm going to move on and define derivative for distributions. Okay, this will be the second section. Second section. Okay. Okay. So second section is about derivatives, and we only focus on one dimension in this lecture, and we are going to generalize it to multi-dimension later on. The reason being that notationally speaking, derivatives in one dimension is much easier to handle. Okay, so as Gondolina probably has said already, the one of the motivation of the distribution theory is to make sense of PDEs where smooth functions do not exist. Okay, so to this end, we have to be able to take derivative of a mathematical object which does not have any pointwise evaluation meaning, and such as the class of distributions. Okay, so the goal is to develop a differential calculus to a general distribution that is compatible with classical derivatives when this distribution is associated with a smooth function, such as a C1 function. Then the definition that will be doing that job is given by the following, right? Okay, so here's the definition. We are given a distribution T, right? This recorded. This is our definition of a distribution. Where we are in one dimension, so I is open set in R. Okay, and the idea of this derivative of a distribution is when it applies to a test function, we are going to define it as negative sign of t applied to the derivative of the test function for any phi in the space of test function. Okay, so this defines the right-hand side defines a finite number because t is assumed to be a distribution, and when phi is a test function phi prime is also a test function. Actually, its support is included in the function itself, in the support of this function itself, and also it is still a C infinity function. So the right hand side is a finite number, so this is a well-defined object. And it is clear that because derivative is a linear operation, it is clear that it's a linear operation in the classical sense. So it is clear that the whole thing, the left-hand side, actually is linear in the function phi. So all that we need to check in order to make sense of the derivative of a distribution as a distribution. So we still need to check a second property, right? So we are going to use proposition 1.5 again to check that this defines indeed a distribution. So here's what I'm going to do. So T is a distribution. Okay, so let T be a distribution. And where then T prime given by this formula, let me call it formula 1, is a distribution. Okay, so as I said, it is clearly linear. And we can verify the second property as follows. So T prime applied to a test function is equal to T applied to phi prime in absolute value. And this is bounded by a C, which depend on the support which we fix in advance. And the supremum of a alpha integer less than or equal to non-negative integer, which is, so let me say k. Okay, so k is non-negative integer, which is less than or equal to a certain m. There exists a c and m such that this inequality, okay, this inequality holds, right? And the derivative, the case derivative of the derivative of phi is the k plus 1's derivative of phi. So we are m plus 1 phi k uniform norm. So we are done, right? So the only thing that's different is here, right? So because we rewrite this derivative as with a one more derivative. Okay, so still this proposition, so proposition 1.5 implies the result. Okay. Okay, so now that we have already defined the derivative as a distribution, next thing we're going to do is to see that actually this new notion of derivative is quite compatible with the classical notion of derivative for C1 functions, right? So C1 functions, we know that what the derivative, the mean of a derivative, we take the limit of the increment divided by the size of the increment, and on the other hand, we also know how to derive a function which is absolutely continuous. This is something done in measure theory. So we are going to see in the following proposition that derivative in the sense of distribution actually generalize these two notions. So the first thing is that so TF prime is equal to TF prime if f is a C1 function in the interval. Okay, and the second one will be so the primitive. Okay, let's do this one by one. So how are we going to do that, right? So recall that this kind of notation, T subscript function always, this kind of notation is always given by this formula over here, right? So let's get back to the business. So TF prime applied to a function phi, by the definition, it is given by TF phi prime. Since we take absolute value, we do not see the negative sign. And so this guy is given by the integral. So with absolute value, F phi prime, right? And next thing we can see is that this F, okay, so sorry, I'm not going to take the absolute value, so everything I say is holds with equality, right? Okay, so this is what we have. And the next thing we do is to use integration by parts for this for two C1 functions with, right? So on the support of this function phi, we use integration by parts formula, and that gives us f prime phi, and this defines, according to the definition again of this kind of operator, t phi f prime applied to the test function phi. Okay, this works for all the function phi, test functions, and so we have the identity, right? This guy will be equal to this guy. Okay. Secondly, we consider absolutely continuous functions, right? So absolutely continuous functions is another way of saying functions of this type. So it's f defined on the left hand side. We have defined functions of this kind. This capital F function. So proposition 2.2, the second item, we consider capital F, which is the primitive of the function f, right? So if we take the derivative in the sense of distribution of the distribution associated with the capital F, we obtain f, right? So this is compatible with the classical derivative for absolutely continuous functions. So now, how are we gonna prove that, right? So this is a proposition 2.2, the second point. The proof of that is so again, TF, let's start from the left hand side. TF prime of that is given by definition this TF phi prime, okay, which is f of x phi prime of x, negative sign, dx. Now we are going to make use of the definition. So there's a okay, the support is included in I, so we do not lose anything to put an I over there. And so now we have actually a double integral because f is defined as an integral from a to x, and f of t dt, and phi prime of x dx. All right. So let me draw a small picture of the function. So x is in the interval, and somehow a is also in the interval. So this a is a fixed point in the interval I, and x ranges in the interval I. So it could happen that x is smaller than I, or x is larger than I. So we're going to split the integral in two pieces. So first piece is when x is smaller than a. So let me denote this interval by I less than a. So this piece is called, let me use another color. So this piece is called I less than a, and this piece is called I larger than a. So when I is less than a, x is smaller than I, so that this x is smaller than I, so that we actually consider the interval xa, right? We actually consider the interval xa. So we change the sign to plus, and ft phi prime x d dt dx. On the other hand, we have this I plus than x larger than a. If we are in the second interval, in that case, we don't change the sign. So x is larger than a, so the interval is still a to x. Phi prime x dt dx. Okay, so the first in the first in the integral, so we're going to handle them separately. So first look at the first integral. We can use Fubini actually. So the observation is that we can make use of Fubini. So we're going to justify it a little bit later by Fubini. So the first integral actually becomes we integrate. So here's how it works. We integrate first the dx. So we integrate dx phi prime of x on the interval. So x, t is larger than x is smaller than t. So phi of t, right? We're going to have phi of t. Okay, on the other boundary value, it is equal to 0, right? Because phi is supported inside the interval I. Okay, so this is the first piece, and we have dx. No, dx actually becomes dt. I less than t. This is it. And for the second part, again, we are going to use Fubini. So this time, still we integrate. So larger than a. So with a negative sign. And so we integrate now the phi prime of x on this interval, right? So it becomes so wait a minute, phi prime of x. So t is less than x, then x larger than t. So we have phi boundary value minus phi of t, right? So the negative becomes a plus. We have phi of t, f of t, dt. Okay, now we can put two things together because this each one of them corresponds to, sorry, this is typo, I less than a interval. Combine two intervals together, we have what we wanted, and this is nothing but TF applied to phi. Okay, so actually it is the same idea, right? So instead of using Fubini right away, with this time we use instead of using integration by parts right away as what we did for the first item of the proposition 2.2, we're going to use Fubini instead, right? And eventually we justify integration by parts formula. Okay, so this says that either way, we have a definition of the derivative for a much larger class of mathematical objects, distributions, which is compatible with the classical notion of derivatives. So this is very good, which makes the theory more attractive. Okay, so let's see now next. Let's see another example, right? So we work out another example. So these are all theory. So now we are going to consider a more concrete example, which is given by this function. So this function, as we can check, it is L1 log function, right? So there's a singularity at zero, but it is really a very weak singularity because it is integrable around zero. So the goal is to compute the derivative of this guy, and this function is not absolutely continuous, right? So we do not know we do not know a priori what it is. What is the derivative of this function, this L1 log function? So the claim is that the derivative of this is given by the principal value that we have worked out in the beginning. So then TF prime is given by the principal value of Cauchy. Okay, so this is very good. How are we going to do that? Let's still compute its evaluation on a test function. So it is given by the integral of log of x, phi of x, right? No, sorry, there's a phi prime. Again, we compute derivative, right? So the derivative of this is given by negative sine of TF applied to phi prime. So this is what we have, dx. Okay. So now still there are two different situations. We are going to split the integral in two pieces. So when x is a negative infinity to 0, we have log negative x phi prime of x dx, and when x is positive, we have log of x phi prime of x dx. Okay, so for this, for the first integral, let's do a variable change. Y is equal to negative x, so that we have infinity 0 log of x phi prime of negative x dx. And we don't want this kind of integration domain, so let's interchange it and put a negative sign. So now we have the domain of integration exactly the same with two different functions. We can put them together. We're going to have 0 infinity log of x times phi prime negative sine of x plus phi prime of x dx, right? And the latter is actually, so this is a trivial step. We realize that the second term is actually the second term. The sum is actually the derivative of the difference dx. Okay, so all that for applying integration by parts, right? So now we have at the boundary value 0. This function is phi 0 minus phi 0, which is 0. And it decays really, the growth, okay, since the function is C infinity and around 0, it behaves like a linear function, which compensates the singularity log x, so that around 0, there's no problem. The boundary value will be 0. And at infinity, because you have a function phi, which is supported in a compact set, so also 0. So it remains only the integral part, which is given by 0 infinity. So 1 over x this time, because it is a derivative for log x, affect x minus phi of negative x. Okay. And we're done, because this is exactly the form of Cauchy's principal value that we computed before in here, right? So this gives the Cauchy's principal value of 1 over x applied to a generic test function. And just finish the exercise. Okay. Next, still along the line of investigating the compatibility of the new derivative, so we're going to show the implication of having a zero derivative. But in the classical sense, when we have a function, right? When we have a C1 function, and we know that its derivative is constantly zero, it actually says that the only possible function satisfying this property would be the constant functions. So it is still the case actually in the sense of distribution. So if you have a distribution that has zero derivative, then the only possibility is that the distribution is associated with a constant function. Okay, so it generalizes again the classical notion of classical implication of having a zero derivative. Okay, so this is the content of the following proposition. So if you have a distribution satisfies that t prime is equal to zero, okay, so the zero in the sense of distribution means that when it applies to a test function, any test function, it only gives the value zero. So this also defines distribution. Okay, so this guy, if it satisfies this property, then necessarily t is equal to t associated with some constant function, c complex value. Okay, so how are we going to prove that? Right. So first of all, we would like to have this property. We would like to have this property t prime equals to zero, meaning that t applies to phi prime actually is equal to zero according to the definition. Right. So now we are trying to find a distribution t such that this property is true. Okay. So one idea to do this. One idea is to do this actually. So we are going to let's say investigate the evaluation of t applying to a generic test function that I call psi. Okay, for any psi. So this I would like to write it as a c times psi. Let's put it that way. Let's put it this way. So for any test function, di, okay, so t applied to psi, we can write it differently. We can write it as psi 1 plus t psi 2. And one of them, say psi 1 is equal to phi prime for some phi test function. And also psi 2 such that t psi 2 is equal to a constant times the integral of psi. Why is this? So the goal is actually to write, to make a decomposition of the function psi for any test function. We make a decomposition in such a way that one piece of the decomposition is the derivative of some test function. And since we know that t applies to the derivative of test function is always zero, which means that the first piece disappears. And the second piece, if the second piece satisfies this property, in other words, t applied to psi 2 gives a constant times the integral of the psi function. We have the t applies to generic test function psi is equal to a constant times this. And this is precisely the meaning of t is associated with a constant function c. So this is our basic idea, right? So make a decomposition in such a way that one piece contributes zero, another piece contributes a constant. So in order to do this, right? So we clearly the second requirement is easier than the first one. So the first one we still don't understand. But the second requirement, the one way to do that. So we can choose as follows. So we can do the second requirement easily. So we can choose psi2 equals to really a constant, which is this constant, which is the constant we want. So the integral of psi we want times a constant, right? The idea is to have this kind of thing. But if we put a constant in here, psi2 will not be a test function. If it is not test function, then this kind of term is not well defined, right? So T is only well defined, is only a well defined object on the space of test functions. So we need to put maybe uh, a test function multiplied by test function so that this guy becomes supported in a compact set. So we have a test function. We choose this like this with psi test function. Then necessarily T psi 2 is equal to T chi, the constant, right? So this integral, right, by linearity. So we are pretty close, right? So this is exactly what we wanted for generic constant. This constant will be the value in here. This will be the value C. So we still need to figure out a way to compute psi 1, and since psi 1 would be psi minus psi 2, so we don't have much choice. It's going to be psi minus the integral psi, this is a constant, times chi function, right? So again, it is a function in di because the space di is a vector space. So in other words, this guy is also well defined. So our goal is to write it as then is to really to choose chi. So it remains to choose chi in such a way that this chi function in such a way that psi 1 is equal to phi prime. Okay, so we don't use any property of chi yet, right? So here we just say that it is a test function in the first step. In here we just say it's a test function. So now we can impose some condition on chi such that this psi 1 is a test function satisfying this property. And as we said, if we have this, we are finished, right? The first one will not contribute, and the second one will give us what we wanted. Okay, so the rest of the exercise is really to find a way, is to find a chi such that we got this identity. Okay, so for this matter, let me just give you a fact. So there's actually a characterization functions which are derivative of test functions. Okay, so let psi be so it's a test function, right? It's di. Then psi equals to phi prime with also phi in a test function if and only if psi's integral is equal to 0. So these two conditions are equivalent. So in order to show that in order to find a chi such that psi 1 is equal to phi prime, it suffices to find a chi such that the integral of psi 1 is equal to 0 according to the fact. And this is much easier to do. Hence, choosing chi test function with the property that the integral chi equals to 1 implies that t applied to psi 1 defined in here gives 0. And this which ending the proof. Okay, so it remains to check this fact. And it is pretty straightforward. So on the one hand, if integral of psi is equal to 0, then let let's say define set phi of x equals to negative infinity x psi t dt. We have phi is a test function because when x is super small, the integral the domain of integration does not intersect the domain the support of psi. So we have the value of phi is 0. When x is very large, so when this x is very large, when it is larger than the right endpoint of the support of the psi function, then we have the integral over actually is equal to the integral over the whole real line, which according to the hypothesis equal to 0. So when x small, x large, phi function is small, so that it has a compact support. And also, it is clear that it is C infinity. And also, it is also clear that phi prime is equal to psi. Okay, so this gives us one direction, this direction, and for the other direction, so we have that psi is a derivative of test function. Then the integral of that will be the boundary value of the primitive, right? So phi of b minus phi of a, and this is actually equal to 0 because, right? So support. The support of psi is actually included in the support of phi, right? The boundary point. So this is really the B is the right hand point of the support of phi, and A is the left hand point of support of phi, which gives us 0. Okay. So this is it. We have shown that the only distribution which has zero derivatives are those distributions associated with constant functions. All right. So one consequence of this is the following. So this is quite an interesting remark, straightforward but interesting. So if we have two distributions T1, T2, they are both distributions, right? With the same derivative, T1 prime is equal to T2 prime. Then T1, T2, right? So must satisfy this property is equal to 0, which implies that T1 is equal to T2 plus a constant, right? So plus a distribution associated with a constant function. So okay, so so this is our remark. So and in particular, so the second thing I would like to point out is in particular that the derivatives as a map is not one-to-one. It's not one-to-one. Okay, as a map from the space of distributions to the space of distributions. So they are off by a constant if two distributions have the same derivative. Okay, so the very last thing I would like to cover is is a very important result, in my opinion. Okay, so it actually it is a quite important result because our motivation is to use distribution theory to study PDEs, and this is really related in that problem. So let me state the theorem. So let S be a distribution. Okay, so then there exists a distribution such that T prime is equal to S. Okay, so this is really a theorem, a result which is in the flavor of solving a PDE. So this is clearly actually this is actually a differential equation, first order differential equation. We're given a function f, s, right? Or more generally, a distribution. It could be a log L1 log function. It could be something. It could be a measure, etc. And we can solve this kind of solution. We can solve this kind of differential equations in the space of distributions. Okay, so this is what it said. Now, how to prove this? So some of the techniques improving the previous proposition actually will be used again. So first, we want to show that T applied to a generic test function prime is equal to negative S phi test function. Okay, so this is the same thing as the differential equation. So we would like to find a T such that this property is satisfied equivalently. This property is satisfied, and again we encounter the derivative of a test function which is well characterized by the fact that this distribution has integral equal to 0. Okay, now how to do that? So the idea is to make use of this S, which is the given value, given either a function or a generic distribution. So S is a generic distribution which is given, and we're going to use S to define T, right? So T, let's say a generic test function, will be given by S applied to a certain transform that I denote by P of psi. Right? Where this P transform satisfies the following. So first thing it should satisfy is that P maps a test function to a test function. It should satisfy this property because S is a distribution. In order to make sense of the right-hand side of this definition, we would like to have a distribution. We would like to have a test function in here. So in other words, P applied to psi should produce a test function as well. So this is the minimal requirement. And the second one, we would like to have P linear, right? If P is linear, then since S applied to this position to this P of psi is linear, we have a linear function, we have a linear form in terms of psi. So this is what we want. This is also a minimal requirement because we want this T to be a distribution, and T, if for T to be a distribution, T has to be linear, and another property, right? So the other property would be continuity, and this is what we want as well. if P is linear continuous, then this definition defines the distribution. So the first two are really minimal requirement, and we haven't said anything about the differential equation yet, right? So there's no reason a arbitrary P would satisfy this differential equation. So the last requirement would be related to that. So if we apply this P, right, in here, we apply this P to phi prime, and we should have, according to the differential equation, when we put psi equals to phi prime, we should have on the right hand side P of psi equal to phi, and this is the third requirement. Now the rest of the game, right? So the name of the game is now to figure out a transform that satisfies the three properties. Okay, so this can be, we have some natural gas. Because of the third requirement in here, we more or less, we are going to guess. If we give it a guess, this P transform should be the primitive of phi, or somehow related to the primitive of a phi. Because when it applies to the derivative of a function, it gives you the function itself. Okay, so this should be related to that. So we are going to try to give it a try in that way. So what if P psi is defined as negative infinity? So it's a function of x, and psi of t dt. Okay, so this is precisely the primitive. If we choose it like this, then the third property would be satisfied and the linearity would be satisfied, but the first one will not be satisfied because the support of this function, look at it, the support of this function will not be a compact set. And to see that, we just think of psi as a positive test function. Then the integral, the primitive of this one, will be an increasing function. And this increasing function will not have a compact support. So we have to change a little bit. So the idea is to subtract a small term, which is the integral of psi, which is a finite constant, times a certain test function chi. And in order to, so a random choice will not do the work because we still want to have a function. The goal is to have a function which is to have a function which is in the space of test functions. Okay, so there's some additional requirement, and what we want is that when what we want is that when it applies to phi prime, it gives automatically the phi function. Okay, the third property is clear, right? So let's check one by one. Let's be more specific. So we checked properties 1, 2, 3, one by one separately. So the first property, is it a test function, right? So when x is sufficiently small, we see that this function is indeed 0, because when x is smaller than the left endpoint of the support of psi and left endpoint of the support of chi, this integral, the domain of integration is not intersecting the supports, so that we have integral 0. When x is super large, we would like to have, so large in the way that it is larger than the right endpoint of support of psi and the support of chi, so that the integral is, when x is super large, then the integral becomes this. Right? It's the same thing as the integral over the whole real line when x is super large. And this is nothing but the integral of psi minus the integral of psi times the integral of chi. And for that to be 0, we should impose the condition that the integral of chi is equal to 0. It's equal to 1, sorry. It's equal to 1. And this is the second requirement, actually, for the chi function. Chi is the test function satisfying this property. Okay. The second property we would like to check is that it is linear, which is obvious. Check. And in order to show that it is continuous, we're going to see in order to show that it's continuous, let's just consider let phi j be a sequence of test functions converging to 0, right? So continuity, we only need to show that it is continuous for a sequence converging to 0 in the space, in this sense, okay, in the space of test functions. We show that we have the following. So P phi j is converging to 0 in di. Okay, if we have this, then we're done with the second point. So for that purpose, we're going to take derivative. Here phi j will take a derivative of this guy, case derivative, and we're going to take the uniform norm. And so what is it? It is going to be the derivative of the first, yes, so it is going to be the derivative, the pk k minus 1, phi j k minus 1's derivative, right? So the minus, this time constant times, again, it's going to be, so there's a j, sorry, and chi k minus 1's derivative. Okay. And we can show that this guy goes to 0. Okay. So the third property is that the third property is clear, because when we apply p to the derivative of a test function, we know that this function must have integral equal to 0, right? And if it has integral equal to 0, this guy in here will be equal to 0, right? So this term actually disappears. So we take we apply it to phi prime. We're going to have exactly the primitive of that function phi prime, which gives phi, right? So the third property is also a easy task. So this finished the proof of the proposition. Okay. So to wrap up, in this second section, we have covered a bunch of important notions. So the derivative, we pass the derivative to the test functions. This is the idea. And we can also define higher derivative. I haven't said that yet, but it is defined similarly, right? We can define, if we know how to define the derivative of a distribution, then we can iterate that procedure to have higher derivatives. And the consequence of that iteration would be a derivative of this kind. And again, it will be compatible with higher derivatives if we have a CK function or if we have a CK function, say. Okay, and then many of the properties or propositions that we said can be generalized. For instance, like this one, if we have the second derivative of two distributions coincide, then necessarily the two distributions are off by a linear function. Okay, so this is it. See you in another video.